Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 39 and we are introducing to you what is known as a MOS capacitor. I'll explain to you the outline of this lecture. We will be dealing with what is the meaning of, first of all, capacitance as applied to a MOS device. We will then look into the capacitance versus voltage electrical characteristics. Then we will look into an ideal CV characteristics breaking into three parts, which is accumulation, depletion, inversion, and then ideal low frequency capacitance versus gate voltage of a MOS capacitor. So let me tell you why this lecture is important, or where will this fit in the whole scheme of things as far as cryogenic electronics is concerned. Please understand that most of the readout circuitry in a quantum processor, in the readout side, which is kept at cryogenic temperature, will require very fast transients, which means that on a real time, on a very short period of time, the readout circuit should be able to understand the state of the qubit in a sense, right? And therefore, the background circuitry or the readout circuitry should be as fast as possible. Now, the speed of the circuitry obviously depends upon the total capacitance the circuit provides to the circuit, because higher the capacitance, more charging will be required to reach to a particular voltage in the output. So, the whole idea is to, can we minimize the capacitance in the circuit which we are trying to propose in a readout, and while doing it we are not compromising on the other electrical parameters. So, that is the reason this chapter is important, and you should also know that when you change the applied gate voltage as well as drain voltage, how does your capacitance change, because it is a bias dependent quantity, right. This one will be nothing to do with cryogenic at this stage. We will go into cryogenic in lecture number 2 and 3 of this week, but primarily we will be looking at 300 Kelvin characteristics. So, those who are uninitiated in this domain, basically MOS cap is a fundamental structure in a MOSFET, right, very straightforward way of looking at it. If you look at the structure of the MOS device, let me use the structure itself. So, if you remember, you had this metal gate here, right, and then you have this oxide layer here, and then you have the semiconductor at this case. So, this is S, this is O, and this is M, and this is where you apply your gate voltage, right, and this is the drain side and this is the source side with metal contact here and a metal contact here. If you remember your basic school level courses, the capacitance is basically two parallel plate capacitor separated by a dielectric. A dielectric can be an air dielectric, it can be a solid dielectric, so on and so forth, which basically an insulator. If dielectric does not make sense to you, simply an insulator which does not carry electricity is inserted between two parallel plates, and therefore if there is a positive charge in one plate, a negative charge appears in the other one, and therefore this way they store a charge. Let's keep that in your background and look at this figure here on the right hand side, which I have drawn. So, this is a positive plate, let us suppose. Here you apply a gate voltage, a DC, maybe let us say a DC bias at this stage. Then you apply, when you apply a positive bias here, this will be positively charged, the metals, and the semiconductor will be negatively charged. This is a p-type substrate for an n-type enhancement mode MOSFET. So, basically this positive and negative charges are separated by this oxide layer here, right, and that makes it work like a capacitor. So, that is also one of the advantage of MOS device, that once you allow the MOS device to work as a capacitor, you do not have to put a passive capacitor in the network which takes more than enough area on silicon. So, a MOSFET can be used as a resistor, we have already discussed that point. MOSFET can also be used as a capacitor. So, this is one of the examples of that. Now, please understand that therefore, the capacitance of any MOS device will depend upon the total charge. The total charge in the semiconductor side will also depend upon not only the inversion charge or the accumulation charge, but also depend upon the interface trap charges. And therefore, when you plot the capacitance versus voltage characteristics, you get many important idea about the trap charges or interface trap charges. That is what written as the second point here. We all know C can be written as dq dV, where dq is the differential change in the charge and dV is basically the differential change in the voltage, right. So, dq dV, and therefore, if you want to find out dq, it is C times dV, and that gives you the value of C capacitance, assuming that capacitance is linear. Again, not true always, For most region of operation, capacitance is non-linear function of voltage. At this stage, we are assuming that the way we are bias the device capacitance is a linear function, and therefore it is kept as a constant value which depends upon the ratio of dq to dv. And this function which c which you get, right, is a small signal AC parameter. When I say small signal, I mean to say that, so what I do basically, I will tell you how we find out is we give a voltage, a DC voltage. Within that DC voltage, we superimpose an AC signal, right. So I have a DC signal here, right, and then I superimpose an AC signal here such that this variation is not more than plus minus 10% of its nominal value. So if the nominal value is say 1 volt, then the peak value can go to 1.1 volt and 0.9 volt here. Then we define this to be as a small signal. Under such a scenario, the capacitance extracted is referred to as a small signal AC parameter, right. It is not a DC measurement, it is an AC measurement which you do. And that is what is written in the next 2 points here. The superposing a small AC signal voltage onto a DC gate voltage is what we are trying to do. And we assume that within the small change in the AC voltage, the capacitance will be linear. There will be no change in the capacitance, and the capacitance will be held constant for the small change in the AC voltage which you see. So what you do, you change the bias and then you check what is the change in the charge which is available on the capacitance side. And therefore, for all practical purposes, that is the takeaway from this whole slide, is that the capacitance value is therefore a function of the gate voltage, right. And this gives you an idea about the total charge accumulated in a capacitor, and also later on we will see gives you much information about the interface trap charges which are there in the MOS structure. Now, let us look at the ideal CV. So, what we will do is, we will do this mechanism which I discussed with you in the previous slide. What was the mechanism? Apply a DC bias, give a small signal AC signal over it, try to find the DC, then shift the DC bias slightly at the top, again you give an AC signal and try to do it. And this frequency of the AC signal can be small or large, right. It is basically low frequency and high frequency extraction of the AC signal of the capacitance. We will keep it small for all practical purposes, but we will vary the DC bias right from a 0 value to a high value, and superimposed on that we will start giving the AC signals, which are basically low frequency and small signal. Initially, since we are doing an ideal CV or capacitance versus voltage, just understand in device physics or in electronics, CV is basically capacitance versus voltage, right. When we say IV, it is current versus voltage. So, it is not current versus voltage here, it is capacitance versus voltage here, and when you say current, I refer to it as current as I, right. Okay. Now, we are assuming that there are 0 charges which are trapped in the oxide layer. So, there is 0, so there is a 0 oxide trapped charges, right. What are these trapped charges? I will tell later on, but just give you a hint here. We have already discussed it earlier also, that when you are actually growing an oxide layer over silicon, you do an oxidation, right. This oxidation can be done in 2 processes. One is dry oxidation, another is wet oxidation. When you do wet oxidation, the speed of oxidation increases, but then the cost you pay for it is that some of the charges or some of the oxidation is not fulfilled, right, and therefore there are some trapped charges which are available in the oxide layer, and these are basically the oxide trap charges which we refer to, right. So, we are not assuming any oxide trap charges currently, and we are also assuming that there are no charges in the trapped layer in the oxide semiconductor interface. In the oxide semiconductor interface, there are no charges available. So, there are no interface trap charges and there are no oxide trap charges. With this, there are 3 operating conditions: accumulation, depletion and inversion. We will go one by one and try to derive the value of the individual capacitance components, which is basically your oxide capacitance, right, the flat band capacitance, your source to drain capacitance, and minimum capacitance as we move in ideal CV characteristics. Let us look at the accumulation mode, right. So, there are 3 modes I told you. Let us look at the accumulation mode now. Now, so this is basically, if you look at the top, this is basically a band diagram of a MOS structure. This is basically a MOS structure. MOS means, if you look carefully, this is positive metal, this is an oxide layer, and this is basically a semiconductor, right. So, this is a MOS. So, this is how we are moving from gate to the semiconductor. So, this side is substrate, and this is basically your interface. This is your silicon dioxide interface, right. And I'm assuming that this is a p-type semiconductor. Why? Because the Fermi level EF, which you see here, dotted blue line, is very close to the valence band, and therefore for all practical purposes, this is basically a p-type semiconductor, right. So, I have a p-type semiconductor. The difference between EF and EV gives you the amount of holes which are there in the semiconductor. So, typically the difference becomes larger and larger as you go into the depth of the semiconductor into the substrate. So, you see the difference actually, you see this is increasing, right, this is increasing and then becoming constant here, but very near to the interface the number of holes are typically very large in number, right. So, let me tell you what has happened in this case. Now, just imagining that on the gate side apply a negative bias, right. I do not apply a positive bias, this is a P. So, this is basically an N channel enhancement mode MOSFET, right. This is an N channel enhancement MOSFET, right, which means that your substrate is basically a P type, and that is what we are starting with. If substrate is P type and we give a negative bias on the metal side, what will happen is that all the holes from the substrate will be attracted towards the semiconductor interface, and that is what is happening here. You see, since it is attracted, the number of holes will be very large here. Not only that, because you have applied a negative bias, MOS side or semiconductor side, the bands will start bending to the top because it is minus Q times V. So, minus of minus is plus, and therefore, the energies will start to increase near the interface, and as you move towards the semiconductor substrate, they will become flat. And moreover, the oxide layer actually goes down like this, right, in terms of energy scale. So, when you plot a MOS structure or a metal oxide semiconductor structure, then you see that there will be a big attraction of holes towards the interface P side, and that causes the upward bending of the bands near the surface. That is what is happening here, you see. And near the interface, the Fermi level is closer to the valence band, implying that your number of holes are relatively larger near the interface as compared to in the bulk. This procedure or this mode is referred to as an accumulation mode, where you are accumulating p-type charges. Let us come to the right hand side figure here. So, this is my oxide, right, this is my oxide, this is metal and this is semiconductor. I have applied a negative bias. So, negative bias primarily meaning that I have applied a potential which is negative, and therefore, there was initially minus Q prime charges were there because of the negative bias, because of which the semiconductor will have plus positive Q charges. Please understand, we are not adding any extra charges, and therefore, the charge neutrality can never be destroyed. So, if I am using a minus Q charge here, I should get a plus Q charge on the right hand side. And then this small blue part of the curve is the one which you actually add up by virtue of adding an extra AC signal to it, because of which you get an extra dq prime here, right. Dq prime is charge per unit area. When you apply a prime, basically it is basically meaning charge per unit area, right. Now, you look very carefully, that blue region is basically I am giving a mod to it. So, I am not interested in its sign at this stage, but effective increase or decrease in the charge is being shown here in this accumulation mode, right. So, because of the large surface hole density, there is an accumulation of charge which is same type, again a sort of capacitance is formed. Now, that is what I was saying, that a small change in the voltage across the MOS capacitor therefore leads to a differential change in the metal gate charge, which is this part, right. And therefore, corresponding to it, equal amount of charge will be available on the oxide side, and that will be positive in nature, and that will be only done through accumulation of holes, free charge carriers which are available. So, if you want to find out the capacitance per unit area in the accumulation mode, then we simply write down Cox equals to epsilon ox by Tox. Why? Because it is very simple, per unit area. So, if effectively the formula is epsilon A by T ox, but what happens is when you do per unit area, this cancels out, and you have epsilon ox by Tox coming into picture, where Tox is this thickness of the oxide layer which you see. This is Tox. So, if you know the value of Tox, you can expect to get the value of C prime, which is in the accumulation region. So, purely therefore, the capacitance per unit area in accumulation mode just depends upon the oxide layer thickness. Lower the value, higher is the accumulation mode oxide thickness. Why is it known as accumulation? Because you are accumulating the same type of charge carriers on the oxide layer, which is basically in this case P type. You can also do and therefore, as an exercise to better understand it, I would recommend that you take up a P channel enhancement mode MOSFET and you apply a positive bias on the gate side, and the expression will still remain the same, the understanding will still remain the same. Just to understand more better, you try to do that part as well in a sense. Let's come to the second mode, which is the depletion mode. So initially it was negative. Now what I do, I apply a positive gate bias on the metal side, right. When you apply a positive gate bias, the holes are basically repelled away from the interface. When it is repelled away, then at the interface the hole concentration actually reduces. And that is visible from the fact that if you look at the Fermi level difference again between the Fermi level and the valence band, this is quite large at the interface and it is relatively smaller at the bulk. So, this is your bulk here, right, and this is your interface. So, at the interface the difference is relatively large, and at the bulk the difference is relatively small, primarily meaning that all the holes which are available at the interface have been pushed back into the bulk, right. And since we have applied a positive bias on the metal side now, again minus Q into V will be the energy, and therefore, since there is a minus sign attached to it, on the oxide layer the bands will be bending downward, and that is what you see, the bands, conduction band, the intrinsic Fermi level and the valence band, they have all bent downwards, right. Now, since the holes have now been shifted away from the interface, this part, let us say very near to the interface, this part is basically they do not have right free charge, they are only depleted. Therefore, this region is known as a depletion density, because it is depleted of any majority carriers. What are the majority carriers? Basically in this case holes, because you are doing a p-type device. Since there are no holes available, it is perfectly depleted. Therefore, we refer to this capacitance as a depletion capacitance, right, and that depends upon XD. XD is basically the length of the depletion layer at the silicon dioxide interface. And that is what I was trying to say, the third point, that the Fermi level moves closer to the intrinsic level, showing there is a weak band bending because of the positive charge near the bulk. At the bulk nothing changes, everything is an interface phenomena in this case, which means that the space charge region XD is primarily a strong function of the doping concentration of the substrate, because the doping concentration of the substrate gives you the number of free holes in the bulk, right, and that is the reason width is equals to XD has been taken into consideration, and storing the depletion charge, right, they are storing the depletion charge in this case. So, you see therefore that in the depletion mode we have found out one important point, that by applying a positive bias we have been able to deplete the holes, and there is a depletion region which is formed near the interface. In the depletion mode, therefore, you see I have applied a positive bias, and therefore, this is my positive bias which I have applied, over which I apply this AC signal to get dq prime, whereas on the left hand side this is my charge, these are depleted charge carriers, right, and this is the extra charge which we get out of it, out of the application of this bias at this stage, right. Now, now you see very interestingly, so there are two capacitances now, one is the oxide capacitance here and one is this capacitance which is depletion capacitance, right. Now, the oxide capacitance, which is this one, and the depletion capacitance, which is this one, are basically connected in series. So, which means that if you give a positive gate bias in this case, then the depletion region will extend beyond a point, the value of your XD, which is the depletion width, will go on increasing, C depletion will fall down, and there will be an inversion layer which will be discussed later on. But for a relatively low values of applied gate bias, you will have a depletion region, and this depletion region will be in series with the oxide capacitance. So, I get the overall depletion here, 1 by C prime depletion is equals to 1 by C oxide plus 1 by CSD, right. I get 1 by C ox plus 1 by CSD, where CSD prime is basically the source to drain effective value which we get. So, I get the overall depletion width as 1 by C ox, because it is a series capacitance. So, if you solve it and do all sorts of manipulation, you can look into this, I get finally my C prime depletion capacitance per unit area and a depletion region to be equals to this quantity here, where XD is my depletion width, which is this one, right, this is my XD, and epsilon S is permittivity of silicon, epsilon ox, which means that C prime depletion, these are all constants, right, we assume this to be constant, though they are not true in cryogenics, but at this stage at 300 Kelvin we assume that all these things are constant, it depends upon T ox and XD. Tox is again constant for once you have fabricated it. It depends upon XD. On what factor does XD depend upon? It depends upon the total amount of acceptor ions which are there in a p-type semiconductor in a MOS device. Depending on that, I will be able to extract the value of C prime depletion, which is basically the depletion mode capacitance per unit area. Let us come to the last part, and that is known as the inversion mode. Inversion mode, we still go on applying much larger positive bias at the metal side. And therefore, what happens is, this is quite interesting, that the intrinsic Fermi level actually goes below the Fermi level of the p-type semiconductor. And that is the reason it is known as inversion. So, what has happened therefore is, till now my Fermi level was closer to the valence band, but if you look very carefully now, what has happened is that the Fermi level is effectively closer to the conduction band, because the conduction band has been bent drastically downwards, and the difference between the conduction band and the Fermi level is relatively small near the silicon dioxide interface, which effectively means there is a large concentration of electrons being generated at the silicon dioxide interface, and this is known as the inversion of the carriers. And this is, and the charge density is referred, the charge per unit area is referred to as inversion charge density. Now, the space charge width XDT remains unchanged. So, there is a depletion width. Within the depletion width, you have an inversion layer being formed, right? And that under small signal analysis, the value of your depletion width remains almost the same for all practical purposes. Now, therefore, a small incremental change in the metal potential in the positive sense will give a small change in the inversion layer charge, right. So, in the inversion layer charge, again as I discussed with you, this is your metal side, this is your oxide, right, this is your oxide layer, and on the semiconductor side you have this inversion layer here and then followed by a depletion layer, right. What is happening is, if you vary the potential on the metal side, then the inversion charge density will change, right. It will go on changing. What do I mean by inversion? I mean to say by inversion is that it becomes as much n-type as it was initially p-type, which means that if it was a p-type and there were suppose 100 holes, all the 100 holes have to be depleted, therefore, the net carrier will be 0 free charge, and then 100 electrons have to be added. That is what is known as inversion. So, you are inverting the surface from p-type material to an n-type material, and that is the reason we define that to be as the inversion. And we here also the inversion charge density is given by epsilon ox by Tox, where Tox is the oxide layer thickness which you see. So, let us come to ideal low frequency capacitance versus gate voltage of a MOS device. Now, what we have plotted here, we have plotted capacitance on the x axis and we have plotted the gate voltage on the y axis, right. And the solid blue curve which you see is basically my CV characteristics which I have plotted capacitance. And their 3 regions are already inbuilt in this section. Let us look at the first region where you have applied a very large negative bias. Remember our first slide in this domain, let me refresh your memory. This is what you do, right. You see this is what you are doing. You are applying negative bias here and you see you had a positive p-type semiconductor being generated. The same thing is replicated here. So, when you are talking about this, it's extremely negative value here, this side, and the value is fixed value independent of the applied gate bias, and it is given by some formula, right, as epsilon ox by Tox and so on and so forth. Then as you start making your gate voltage more and more positive from the negative side, you start entering into the depletion region, right. And I will tell you how it works out. There are 3 regions, we will go one by one. This is pretty important and you should be very careful in understanding it. Okay, now more importantly, depletion we can see later on. Let us look at the inversion one, right. So, this is a strong inversion again this side. So, these are 2 extremes, one is the accumulation, another is strong inversion. It is easier to look at strong inversion first and then we will come back to depletion. In the strong inversion, my gate voltage is much higher as compared to my flat band, which is 0 volt or minus VFB because it is a p-type semiconductor. It is a very high value, it is more than the threshold voltage, inversion layer has been formed and I get a fixed value of the layer, and that happens to be again Cox only, because the inversion layer is so thin that it actually screens the depletion layer, and therefore, the original oxide Cox which we were getting, oxide layer per unit area, let us suppose, in strong inversion becomes almost equal to that of the accumulation. So, you see this value here and this value here are almost the same, and the reason is in strong inversion region, you will always have a thin layer of electron, sort of acts as a screening effect, gives you a screening phenomena. Because of the screening phenomena, the depletion region part is not being able to talk essentially in a very layman language with the metal side, and that's the reason it's almost just like an oxide capacitance which you see in any other case, like when you're seeing in the accumulation region. So you have this here and you have this here on this side, right? They're quite almost equal to each other, which you see. This part we will discuss in the next lecture. So let me recapitulate what we did in this half an hour. We explained to you the basic idea of what is the meaning of capacitance, small signal capacitance. Then we understood what are the various operations which are there in a MOS capacitor, looking at the band diagram. And then there are three regions of operation: accumulation, depletion and inversion. We also understood how the width of the depletion region changes with bias and acceptor ion concentration. And finally, we looked into the ideal low frequency capacitance versus voltage gate characteristics, within which we only just looked into accumulation and strong inversion. We will be coming to moderate inversion and depletion in our next lecture. I hope you enjoyed the lecture. We will meet next time more with depletion and moderate depletion regions.